I will just summarize what was said before. That we have a genus, which is a homomorphism from cobordism ring to arbitrary ring, probably Q or Z with 2 inverted or Z with 2 inverted and some other additional variables. And we noticed that since this cobordism ring, in the cases which I considered were generated by the projective spaces, to know this homomorphism, it was enough to know the values on the projective spaces. And I defined just generating series of X, and it tells me the values of CPN. And also there's another sequence, f of X, which is X divided by G inverse of X. So this was the form X plus higher degrees, and this is of the form 1 plus higher degrees. And this, so this is to know what are the values of CPN. And if you know, if you have arbitrary manifolds, so to know what is the genus on that, you integrate the characteristic class associated to this function. So this is to compute P of M from chain classes of PM. Okay, so I got used to work with complex manifolds. So then you have chain classes, and for the non-complex, like oriented cobordism, you use Pontryagin classes. It's exactly the same construction, but there are small, minor modifications. So this is one, what I said, the theory. And later I moved to elliptic genus. And there is a fragment that I planned to talk about, but I think because of time, there is no chance. So you have genus. So I just tell you what are you missing. There is cohomology theory, so generalized complex-oriented cohomology theory. What is generalized complex-oriented cohomology theory? It's a generalized cohomology theory. So of every topological space, you can compute this cohomology in this theory. Also homology, because cohomology comes also the dual variant. And what it means complex-oriented? Complex-oriented, that every complex bundle has orientation. Orientation is an element in cohomology, and most important are the orientations of the linear bundles. So this first chain class, so it has first chain class or the Euler class. It's different than the usual one. If you map complex-oriented theories, it's not true that one chain class goes to another. It's rather the key point that chain classes are not mapped. They are the relation. For example, in K-theory, the chain class of a line bundle is 1 minus L dual. And by the chain character, is mapped to 1, something that appears in these characteristic classes that we discussed in the top genus, for example, something like that. And also there is a formal group law. So this is something that tells you what is the chain class of the tensor product. F of chain class of L, chain class of K. So this is some formal power series. So C1 maybe. And from this formal group law, you can go back here to the this generating function G, which are called logarithm. In fact, there is notion of logarithm in the theory of abstract formal group laws. So anyway, these three components are somehow related, and this is the best situation when you have generalized cohomology theory, because you can form formal group law, and also you can define the genus. This is, you take 1 over M and you push forward. Then you have some kind of genus. So this is ideal situation when you have generalized cohomology theory, you have genus and you have formal group law. And the story was that when the elliptic genus was invented, there was a question whether elliptic cohomology exists. And by some abstract nonsense, you can, having a functor, having phi, which is mapped from the cobordism to R, you can define a cohomology theory over phi with R. So this is for any space. This is a module over cohomology of a point, so you can produce such a thing. And this is question: do you get a cohomology theory? And this problem with exactness, and it was solved by Landweber, Ravanel, and it was. And who was the first? Third author, I forgot.
Was it Stone?
What?
Stone?
Stone, yeah. Okay, so anyway, you have full package. Complex oriented cohomology theory called elliptic theory, formal group associated, and genus.
Sorry, the formal group, is it too naive to think about this as a sum of gem classes? Or
So the formal group law is the following for the usual cohomology. Just formal group is a formal power series into variable. So this is for the cohomology. For the case theory, it's something like x plus y. It has to be in the beginning, minus xy. And for the elliptic, it's more complicated, which if you wish, I can. It's related to Euler addition theorem of elliptic integrals.
But the result of this Landweber is that the answer is yes, that it's always
yes. Yes. And I think in the first approach, still 2 had to be inverted. And further there were some refinement, but I'm not sure about the details. But it was still in these years, like 88. So preprint was, I think, from the 88, and then it was published a little bit later, something like 5 years later. So in 88, it's already quoted, but really published later. Okay, so this is the general setup, and now we were talking about rigid general. So there was a question whether phi genus of the total space is the same as the genus of base times genus of the fiber. And in general, this is not true. Only for very few general, this is the case. And also, I was talking about equivariant equivariant rigidity. And maybe I said it's, I made a mistake saying last time, the Hirzebruch Chi genus is rigid. Which is, how to write it? sum of Euler characteristics of n with coefficients omega p. So this is chi genus. This is rigid for the case when the F is a bundle associated to a principal bundle with G connected. And I was misled because I got used to the algebraic geometry, and this is also more generally rigid when you have the bundle which is trivial, locally trivial in Zariski topology. So this is another concept. And this Hirzebruch genus is the general form of the rigid genus. And so now there was a question about elliptic. This is genus is rigid with respect to F being a spin. In the above sense that you have to have a principal bundle and associated bundle of manifolds, and then the result of Oshanin that this form G of x, the elliptic integral from 0 to x, and then 1 over 1 minus, and where is epsilon, where is 2 delta x squared plus epsilon x fourth. Okay. No, I cannot write like this. Okay, and from that, immediately get values what is elliptic genus of Pm.
So if you got a square root of t squared?
Yes.
That's a delta.
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 Here. Delta t squared. So if I take 2n, okay. So in general, when you have any kind of genus given with this logarithm, so to know the values of projective space, you have to differentiate this formula and you get coefficients. And here every second will vanish. So I just CP2M. This is coefficients of at x to the power 2m of this function. Square plus epsilon. Okay. And now comes surprise. Maybe you know what are the coefficients of that function. So this is really
of the integral, not of the.
No, because you maybe I should write it here. That g of x was a sum value CPn divided by n plus 1 c to the n plus 1. So really, if you integrate, you get this coefficient.
I see. The rest.
Yes. And now there is a mystery behind it, because elliptic genus was proposed by physicists like Witten, maybe some others before him. So it comes from some vague consideration. You cannot trust really what physicists say, and their computations are really, they break any rule. Okay. But it turns out that comes something very beautiful. You get this formula, and you can check it even in Wikipedia that these are of okay, if I plug in epsilon equal 1, then will be then I would have yes. So these are Legendre polynomial. So it's a mystery. Why do you get Legendre polynomial? And if your epsilon is not 1, you have to somehow homogenize. So from some these strange reasonings, you get very decent and in fact very classical mathematics, something like 19th century or even earlier. Okay, so as I said before, so this formula, so y squared equals 1 minus 2 delta x squared plus epsilon x to the 4. This is an elliptic curve with undefined, identified 2 points. So it corresponds to some parameter q belonging to the upper hyperplanes, or you can say that not q, tau, and q is defined e 2 pi I. Yes. Okay, so there is an elliptic curve corresponding to that, and I will write down a formula for this inverse function, that function that allows you to compute elliptic genus. It will be some expression. So maybe I should give a.
Sorry, can you explain a little the meaning of delta and epsilon in the original problem?
The original problem first are just numbers,
Yes,
or rational numbers. Later we treat it as so for this there are numbers, but later we'll treat they as a variables.
Yeah, but in the original problem of computing the elliptic genus of the vibration, what do they correspond to? I mean, so these are the inputs that you have to put.
No, I'm asking about all the genera which are rigid in that sense.
Ah.
And I answer is, for example, genera with values in rationals.
I see. So
and I get this answer.
So, okay.
And then, okay, this answer depends on 2 parameters, and then I treat them as 3 parameters. Okay, so now this is, maybe I stated in the formulation of Don Zagier, but maybe I just quote Nowski. So there are two brothers Udnowskis, so square, but I will follow just the formulation of Zagier. Zagier, I should say, I don't know. Then this f of x is so this is what appears in the Dirac operator, and then there's a twist. And this should be taken with alternating signs, so -1. So for even n, this is in the denominator. For the odd n, this is in the numerator. So this is a computations coming from the theory of elliptic curves. That this elliptic curve, this is the inverse of the function. And it's a computation, and maybe what is the relation with these numbers? So delta can be related to Q as the, for me these are still magic formulas, but this is kind of one of the modular forms. And epsilon. These are some modular forms that I will not speak about. So there is a relation between between Q's and these numbers, and you get answer. So now we switch from this world when you have epsilon and delta to the epsilon and delta were parameters, and now Q will be parameter, and depending on Q you have function that can serve to compute the elliptic genus.
So now you went to a one parameter family, so because there is a relation between that and epsilon.
As a modular form, they are independent. Yes.
Oh, I see.
Also here you can treat it as a real, and this is complex.
Ah, okay.
Okay.
But if I pose epsilon equal to 1, I get the Legendre polynomial for that elliptic genus.
Yes. Yeah, but then setting this one
to 1 is like great.
or rather classically that if you set epsilon equals 0, then you get more or less the Hirzebruch genus. Okay, so now we leave epsilon and delta and we stay with Q. And I will transform this. So this is original formulation of Don-Zagier. And now I would transform it so it would remind the formula for the operator, for the index of the operator. Maybe. So first there will be some component of this, 1 minus Q to the nth power. Once in the denominator, other one for other cases in the numerator. So maybe I will just not care too much about. Oh, so there was a line here.
It's okay, it's okay.
Here?
No, it's there, it's still there, almost there.
Okay. So maybe I just type it like C of Q, then X over 2 hyperbolic over Q over 2, and then numerator is Q odd, 1 minus Q and P X times 1 minus Q and X, and in the denominator the same. What's the Q odd? Like isn't this a not to n odd? Ah, okay. And even the same. So now in the sources there are two approaches. One you take Q, and in other sources you take Q square. So I would switch now to other notation. Then Q is Q square. So I would rewrite it, this part.
Can you write this in e to the 2 pi I tau? So
What?
Q is not e to the pi I tau? Or?
Yes, maybe here was e to pi I, yes, pi I tau, and here will be e to 2 pi I tau. Now it's better. Yes. Every time I take a square of Q, I mean that I have in fact tau, and I multiply it by some. So in this new notation, it would be still C over Q. And then you have an odd, so the product maybe not keep this notation. Okay, so this will be for n from n greater than 0, 1, Q to n plus 1/2. Half e to minus x. This is in the numerator, and in the denominator Here's just n greater than 0, 1, x. Okay, so now you have this power half. So maybe just to have it q to the power half, it will be just new variable. You can call it y or e to 2 pi 2 pi I z. So z is tau by 2. So I introduce this new variable, and maybe I skip further. So you just here instead q to power n plus half, you just plug in y. Okay, but maybe to make it short. So let's define theta function. Jacobi, this is classical Jacobi theta function depending on t. So on the parameter tau, so x. This is where I have this definition. There should be some coefficient which will cancel out, but maybe let's write it for the. And then you have infinite product from n equals 1 to infinity. 1 minus qn, 1 minus qn. 2 pi x times the same with minus. So you can reorganize these products to another form, which would be C of Q.
Sorry, what is, these are definitions of C of Q in different cases? This,
you can trace it.
What is C?
Here you have alternating product of this. 1 minus Q to the n. Anyway, this is something,
Is there an equality after C of Q? Is there C of Q?
No, before C of Q, because it's just f of x is this thing that you write.
Oh.
So maybe you should write the equality before C of x, because it's f of x, right? F of x is equal to this.
Ah, yes. This is what you want. I just transform this. And then f of x is this constant depending on q, and then I have just theta function here, theta, and I plug in the 1/2. So this is a formal power series. Formal power series in Q and also in Z. And it has especially nice formula when I a little bit change this constant. And this is Zagier function. I do not care, for the moment, I do not care about this constant, because after normalization, I get a better one.
So Q and Z are therefore not independent, right?
Q, yes, they are dependent, because Q is e to 2 pi I tau, and Z and
I thought one was. I
no, I took the square.
So Z is the old Q.
No, this is new Q.
New Q, square root of. Oh, no, okay.
No,
Z is
square.
Yes.
I took square, and that's
old.
why I got half integers,
Yes.
and I separated this half integers.
Y is the old Q.
Yeah,
It doesn't matter. Y is equal to the one.
I think it's okay. But anyway, better to see by yourself and do this formula. But what is the conclusion? I take a slightly different normalization. Zagier function, which is I take f, say a, d, depending on tau, which is a plus d divided by a, d, and here so that's why I do not care about this constant here, and also this one. It's not interesting for me because I take such a quotient and they cancel. And what is written here is up to a constant, just f of x minus z, up to some constant. And this Zagier function has a beautiful expansion. So maybe f tau a d. This is maybe this is too much. Maybe I would say A is A, D. So then this is one inverse. So this is constant term, and now comes the higher terms with respect to Q. Yes. Q to the power n for n greater than 0. And what is here? I should take a sum of the divisors of n. So maybe k times L equal n, and here a to minus k, a to minus b2 minus L minus a to k b2. So this is a coefficient in front of Q. So you can plug it to some calculator and write in the extension. So now first you have, and it's important that this function has a nice transformations. With respect to a modular group. First of all, if I add 1 to A or 1 to B, then it doesn't change because it's expressed in the terms of exponent. So F A, B, maybe this is also the symmetric, A. This is the same as the F A plus 1, B, and so on. Also, F of A plus tau, B can be expressed as A, B, and here comes not enough space. minus q 1/2 e to 2 minus 2 pi I. No, it's not the stage. Wait, I don't remember this transformation rules by part. And you have the same D, the other part, and then so you can say that this function has this periodic transformation, but in other words, more geometrically, this is a section of some bundle over products of a curve. Section of a bundle, of a line bundle over E square, where E is C divided by the lattice, generated by 1 and tau. And there is another transformation with respect to change of tau. I don't know how I'm with time. Maybe it's important.
It's the same. It's wrong.
Maybe I say it works. F1 plus tau is the same as F tau. And also, it's important to say what's happened if you change tau inverse. B divided by tau. And here I should divide by tau, because these are parameters of the curve with changed parameterization. This has this kind of transformations.
It should be F minus 1 over tau, right?
Yes, minus, yes, because it's in the upper. That's right, it's written in my notes. Okay. So now, so you, okay, so maybe I will repeat. So the elliptic genus of a manifold M is an integral over M, and then you take this function. I have this x here, which was somehow forgotten in this. Ti, and then f over also there is a problem. If you look at the Chern classes, you apply Chern character. This is e to the power t, and here in this convention you have 2 pi I. So I have to take Ti divided by 2. Oh no, okay. And then I take integral over M, and here I should take a product over Chern roots. Maybe I computed for the complex.
So I thought your parameters are little ab. So there's in your f of ab, you had.
No, I transformed that one. And there should be x. It's forgotten. This x is here.
Oh, I'm saying here the big F, the parameters are little ab, but then these are not the Fourier coefficients, right? So shouldn't it be tk divided by 2 pi I?
Well, anyway, I want to plug. Oh yes. Okay. Yes. Okay, 2 pi I minus z. This is the formula. Okay, and I take a Chern root. So this is a formal operation. Then, so if the line bundle decomposes into linear terms, you take the pk Chern of this linear component. If not, then I do it formally. It's a symmetric function. So I integrate it. And if I want to compute for the real manifolds, real spin manifolds, then I use similar things with Pontryagin classes, and then plug in minus z minus 1/2 tau. So in fact, we have two kinds of classes. One for the complex, when the z is a free variable, another for the spin manifold that I plug in only the special value. Okay, and maybe now I would.
Sorry, can you recall what are the decays in terms of the manifold?
So decays do not exist. This is the answer. But if they existed, then product over 1 okay would be the sum of the Chern class. Okay. Yeah. So this is a formal construction. And all topologists maybe can say the bundle doesn't split, but if you pull back to some other space, it splits and take a valuation there, and then you show that it lies in the image.
So a few questions just to be sure that I am following you. So why do you need to distinguish these two cases for fx? What is the so why fx has these two possible?
I think it's the same form.
It is the same formula, or
this is the same formula.
Okay, just in different variables.
Yes, because I just yes, this is the same formula. Because
so the first line and the second line are the same formula in reading.
Yeah, maybe I can write it y and also y here, and if you transform it, you get something like this.
Okay, and what is CQ? Can you say it again?
What is
CQ? C of Q.
I could trace it here. Q is a product of 1 minus Q square by product of 1 minus Q square, but here is odd and here is even. So this was in the original, but if I use this function f, this constant is changed. Because this issue of normalization of the genus, and this normalization is bad. And how on? Okay. So I have three things to say. One, maybe this is just matter of transforming this formula. So if M is complex, or M complex. Calabi-Yau manifold. Calabi-Yau manifold, there are many definitions that are not compatible, but for me it's enough that first Chern class of M is 0. So this corresponds to the sum of Pi's is equal to 0. Then these transformations, if you look at the transformation here with respect to tau, something appears here, this factor, and this factor, if you apply in this integral, if you replace tau, it will cause, this factor will appear as many times as you have Chern roots. And if you know that the sum of the Chern roots is 0, then this factor will cancel. And the corollary from that, maybe I just type this original elliptic, unnormalized elliptic genus of M is a should I give the proof? Maybe in words. Weak Jacobi form of 0 and index maybe I will not translate this sentence. This translates to the fact that it's a weak Jacobi form, translates that with this transformation, you don't have the factor here vanishing because C1 cancels. The sum of the term roots cancels. So if you, from every TK, you get a factor and they will cancel. So this means that it has a good transformation properties with respect to the modular group. Okay. And if, or maybe I just write down there. This is for this unnormalized M, and here this is Z tau. So I plug in Z over tau minus 1 over tau. This is the same as E. I believe normalized. Yes, this is exactly the same. And if you twist it by this factor that I introduced here, you would get that. So
sorry, is this the defining property of being a weak Jacobi form? I don't see what it, so what is that?
I don't want to write down this one just to take. So the
yeah, but I don't even. What is E? I don't even understand what it is.
no, so sorry. This is elliptic genus. Yeah. So this is a function in Z and tau, and it transforms in that way. If you change the parameter of the elliptic curve in that way that you take inverse with minus, and here also change the parameter, so then this normalized elliptic genus will stay the same. And also there is another...
what is the relation between this property and the notion of weak Jacobi form? Is there a relationship or not?
Yes, so this is a part of the definition.
Okay.
And also there is a rule, what happens if you add 1 plus to tau, so it stays the same. And also Z, if you, it's invariant with Z. With respect to adding a lattice, that means adding to 1 and tau. And what is the difference between this and this normalized? So this is somehow, this is somehow better transforms because there is no twists. On the other hand, that one is better from the point of view that is holomorphic with respect to a parameter Z, because you have here, or maybe I should say, this unnormalized connected with normalized. I take unnormalized, and I have to take it 0 divided by. So it has a pole with respect to Z, but so this.
That's the power of the dimension of everything.
Yes, power of the dimension. So this is holomorphic, and this has a better transformation properties. So this is the only difference. This is matter of normalization.
So before, for an arbitrary complex manifold, you have said that the...
For arbitrary complex manifold, I can define it, but as soon as this is not equal 0, the transformation rules are more complicated, and then you get quasi-Jacobi form.
Yeah, my question is, before, for an arbitrary complex manifold, the elliptic genus, so this construction was defining a section of alien bundle over this product of elliptic curves. What in the case of Calabi-Yau, does this section have special properties?
Yes. Because each dysfunction, F is a section of some boundary.
Over an elliptic curve.
Yes, over elliptic curve, because we go down to one parameter.
But this was over a product of two elliptic curves.
So one is parameter z or minus z, and another you plug in a cohomology class, and then integrate over this.
So it's, in the case of Calabi-Yau, does this section is only over an elliptic curve or over a product of two elliptic curves?
You get rid of one variable, integrate. Okay. You integrate over cohomological variables.
Now, so this transformation property, what does that say? Tell us about cobordism classes. That everything was built out of. I mean,
okay. So if you are in the world of Calabi-Yaus, then you can say that the elliptic genus of the Calabi-Yau is the weak Jacobi form, and you know how ring of weak Jacobi form looks like. This range of weight and index. So it's generated by 3 generators as a polynomial. So in fact, you can compare this elliptic genera, and then you can compute, for example, the initial part of this extension. Of this expansion, and you find out that it has to be equal to some combination of Eisenstein series. So there are exact formulas. Maybe, no, I will not write it now because, and
I mean, does this give us any, I mean, what does it?
So maybe I should now quote the Totaro theorem, that if you take there are so-called flops in algebraic geometry. This is operation on the complex manifold that you can blow up something and shrink in other direction. So Totaro theorem is that exactly the kernel of the elliptic genus is generated by this kind of operation. These are called flops, but even more. Totaro says that whenever you have X, which is singular, and you have 2 resolutions, they are called Crepant resolutions. So when can you apply this situation? When X is singular, but if it has a so-called canonical bundle, which is extension of the top dimensional forms. If this is a bundle, and it has a property that if you pull back to the smooth, it's still the canonical bundle. So then this resolution is called Crepant. So Totaro proved that x1 minus x2 in the kernel of elliptic genus, and this kind of generates. The flops are the special cases of the 2 Crepant resolutions.
So does it mean that 2 Calabi-Yau 3-folds are cobordant or bordant if and only if they're related by a sequence of flop transitions?
No, it says that 2 Calabi-Yaus have equal elliptic genera if they can be joined by the sequence of flips.
And the elliptic genera is, I mean, does it exhaust all possible invariants of Bordism?
No, the Bordism genera are much bigger ring. It's infinitely generated. So it was rather the problem of this, that you have first Hirsebruch genus. It somehow kills higher generators, and there are only 2 left. And now elliptic genus is another invariant that leaves you first 4 generators and kills higher. So if you live in the worked with manifolds, complex manifolds of dimensions smaller than equal than 4, then nothing is cured. But if you go higher, then something, then elliptic genus does not distinguish things that are not covariant.
Is there, now that you mentioned these flows, is it known what is the behavior of the elliptic genus if you do a conical transition? So if you construct some rational curves and then you smooth out instead of doing a
well, the classical flop is just a cone over P1 times P1.
Yeah, and if instead of calculating a small resolution of the singular object, you smooth out, you calculate a smoothing. Is it know how the elliptic genus changes?
So this is in fact the work of Borisov Lipkover, that they define elliptic genus for any kind of singular space, but even more, they calculate elliptic genus for singular pairs, that manifolds modulo boundary with some coefficients. And they define this elliptic genus in the way that they resolve. So upstairs you have a manifold with divisor, normal crossing divisor, and there are some coefficients associated to divisors, some multiplicities, discrepancies of this resolution. And from these numbers, Borisov and Lipkover define some elliptic genus, depending on the resolution, but they prove this does not depend on the resolution. Just checking how it looks like with one blow-up. So maybe it partially answers your question. Whenever you have some blow-up of some singular things in two ways.
I'm asking about if you have this situation of a flop for Calabi-Yau, then another thing you can do is now take the singular Calabi-Yau and smooth out the points. So you transform any conical point by adding some variable.
So this is what Borisov Lipkover says. Whenever you have X singular and maybe with some divisor, you go up. Here. And they show that elliptic genus of this pair is the same as the elliptic genus of that pair. But in the case when this is discrepant resolution, these divisors are 0. So in this case, elliptic genera is well defined for the singular space. And even more, not only for singular space, but for a singular pair, because you can, sometimes it's more convenient to have.
I'm going to ask in a different way. If I do a deformation of complex structure of X singular, do you know how the elliptic genus changes? To a smooth object,
to a
deformation of complex structure.
You mean deformation in a family?
Yeah.
No, this I don't know.
Okay.
This I don't know, and I haven't seen. No, I was rather thinking about smoothing in the sense of taking resolution. And the decrepant is the special case when this contribution of the boundary is 0. And one more time, I should stop now. So I think I have 2 topics left, which I will not.
But I think you started 2 or 3 minutes late.
Okay, so in one, what is relation?
10 seconds. It's fine. It's fine.
10 seconds.
Okay. No, 10 seconds. So if you look at this formula, so we can index. So take.
If you can write a little to the right, that's better for the camera. So.
The right one. Here?
Just put yourself
okay.
right
Okay.
where.
So maybe I make a.
We'll give you 10 more seconds.
So we can index. So take a bundle. Maybe first I introduce a notation. C E of a bundle E. What is this? The direct sum of symmetric power of E, okay, times T to the K. So this is formal combination of bundles. And the same with exterior power. here you take an infinite series, and here you take just a finite number. So if you take, and if you take the Chern character of that. So then you get what? This is a sum t to power k e to power c1. So take e equal line bundle. Okay. This is infinite series. This is 1 minus t to e to c1 L. And this is nothing but 1 minus t c1. So if you look at this formula, you see the same things here in the numerator and denominator. And then you have to say what is the line bundle. The line bundle that we can took is here. So take a line bundle, which is in this first notation, what you take tensor product, infinite tensor product with half integers of the bundle lambda q to the power k tangent bundle m tensor, infinite tensor product for the symmetric power q to L. And if you apply Chern character to that, you get exactly one of these formulas. So then the corollary is that the elliptic genus compute the index of twisted Dirac operator twisted with this bundle. So you have to see exactly that this summation is with good indices. That takes some time, but this is so if you call it L, some very fancy script L, so then less fancy script L of M is the index of the Dirac operator twisted by L. And for the complex case, you have extra variable y, which is not necessarily specialized, and then you get more two variables here. You should take tensor products of exterior powers and exterior powers of the dual. You cook up some expression and you get exactly this complex index. So one subject is left, that what is the relation with the loop space? But I would skip that.
I have a question. What is the relation with the loop space? Can you say something? Sorry.
Okay. I'm very glad to answer that question. So for the loop space, I use the localization theorem. Whenever you have some manifold n, and I want to integrate over n some class alpha, and everything is equivariant with respect to action of the circle S1. So this is the same as integration over fixed points to a circle, and then x. So maybe I do it so. But it will be just one line. So M is the fixed point of the action.
Because the fixed points are basically the constant loops.
Yes. This is exactly. So fixed M. And then here I have to plug in Euler class of the normal bundle. Yes, and I take N, the loops of M, which is mapped from S1 to n. And of course, circle acts are free loops. You can rotate loops. And the fixed point set is constant loops. So what is the tangent space of n restricted to a point, to a constant loop? So this is a map from S1 to Pn. This is other representation is a direct sum over integers Tn twisted by a character which I will call Q. Q2. And now I would like to compute alpha just formally. This is Hirzebruch. This is short. I want to compute a local contribution. Local contribution of chi y of the loop space coming from n. So I should take an infinite product over n divided by c, and then 1 minus, in fact, I take minus y to be 2 e to minus I y q. And this is a product over roots, I term root. And now this is something that maybe physicists like to do. You have infinite series, which is not convergent. So you somehow pair it odd with positive things. So you have two factors, one with okay, and this is Q to n. And you couple with n and minus n and transform it, and you arrive exactly to the formula for the theta function. So this is more or less. So Witten did it in an illegal way that at some point he had to rise. There was a factor 1, y to 1 plus 1 plus 1. Infinitely times. So he said that this is y to the minus 12.
But there is approximation, yeah.
But there is a way going around that. If you you just normalize. If you normalize, then you get rid of this factor. And if you normalize, so you have summation that is acceptable for the civilized work.
Thank you. We're running a bit late. I don't know if anybody has more questions.
So you could also put vector bundles on the same.
Twist everything by vector bundle.
More general vector bundle.
Yes, I think I can twist by the vector bundle. In fact, in this Borisov and Dober earlier paper, they twisted by a power of the canonical bundle. Yeah. That produces something significant, but I'm not sure what is. For Calabi-Yau, it doesn't matter because it's trivial. Maybe for non-Calabi-Yau, you can untwist it to get better transformation from it.
Oh yeah, maybe. Could you explain again that notation with the direct sum of Tn tensor Q to the n?
So formally, tensor by representation C with Q. So this is a representation of C1. of a circle.
Yeah.
Of U1.
Yeah.
So it can rotate with some speed. Or maybe I should explain it. So this is Fourier. So if Tm was one-dimensional.
So Tm is TPM here, right? At the point.
At the point, yes. So what is map from C1 just to C? What is this? This is something spanned by the functions e to, how to write it? By a character. Okay.
Yeah, it's clear.
Yes. Yes. And additionally, you have tangent bundle. So except that one, you have chunk character coming from this splitting. So you have, maybe I should here, this one treat as a one character. And then it's very formal. I think it's not mathematical statement here because there's no notion of the Hirzebruch class of infinite dimensional manifold. This is heuristic, purely heuristic.
Just thank Andrzej again.